Empirical formulas are the last topic I'm going to cover before the test. All right, and you might say to yourself, but I already know how to do empirical formulas. And you do. Let me show you some. Whoa, that's not it. Don't copy these. Just watch. This is an empirical formula. Don't copy this. So is this. So is this. They're all empirical formulas. Okay? So is this. Basically, they're all empirical formulas. Well, we've been doing that for 2 weeks. Why do I have Roman numeral 6 empirical formulas? Because now we're going to do it backwards. We're going to do it from laboratory data. If I told you how much of an unknown compound, how much of an unknown compound consisted of aluminum and sulfur and oxygen, could you work backwards and tell me what the formula that was? That's actually what you do in forensic science a lot of times. If there's an unknown powder, an unknown substance found on a body, you want to know, is it a poison? You know, is it cocaine? Is it a drug? Okay, or is it just baby powder? Okay, you don't just assume it, and you don't do like they do in the movies and taste it. All right, you send it to the lab, and they run an analysis on it. Most of this is done nowadays by machine. However, if I give you the information, you can do it by your little machines in your head. You can actually figure out what that compound was, the empirical formula of it was, backwards, using what's called experimental data, basically lab data. We're going to do that tomorrow. Tomorrow, I'm going to give you a compound. You're not going to know the formula. You're not going to know it. You're going to do a simple thing to it, and then you're going to be able to tell me the correct formula for that hydrate. All right? Okay. Well, first of all, let me give you the definition of an empirical formula. It basically is, as you saw a minute ago, H2O, CO2, all these guys. It's the simplest whole number ratio of atoms in the compound. This is 2 to 1, 1 to 1, 1 to 2, whatever. It's the ratio of atoms. It tells you what they are like, okay? And so that's the definition of an empirical formula. You've been writing them using the periodic table and the octet rule. We're going to do it backwards, okay? It is simply the simplest whole number mole ratio of atoms in a compound. So you've seen these before. You know how to write them using the periodic table. I'm going to teach you today, with 2 examples, how to do them using information. The percentage or the mass of the different elements in that compound. You can tell me what you have. I will tell you it's got 27 grams of sodium and 42 grams of oxygen and 12 grams of hydrogen. What was that compound? And you could actually tell me what it was. All right, here's how you're going to do it. Copy this example now. I start off with a really easy one. And then I'll do a much harder one that has probably about 4 different things that makes it more difficult, or at least more different than this one. This is about as easy as it gets, as you'll see in a minute. All right, first off, a minute ago I said the empirical formula is the simplest whole number mole ratio. Mole ratio. Do I have moles up there? No, I'm giving grams. So what will I do? Do I know how to convert grams to moles? Sure, that's going to be my first step. I'm going to convert each of those masses to moles, because that tells me the actual formula. The moles mimic or mirror the atoms, okay? Simply 6.02 times 10 to the 23rd more of them than just one atom. Okay, that's what a mole basically means, that many atoms in a mole. So I'm going to convert each of these guys to moles. Let's convert my tin to moles first. We'll start with tin. How would you do that? How would you convert 39.4 grams of tin to moles? You all know what you do. What would you write down first? What would you write down first? 39.4 grams. And then you would multiply by what units would go on the bottom? Grams. Top? Moles. 1 goes next to moles. 1 mole contains how many grams of tin? You look at the periodic table. Periodic table says it's 118.71. and then you do it. Now, by the way, don't get your calculators out yet. You'll need them later. But that, I have this one already worked out for you. There it is, 0.332. All right. Let's do the same thing for oxygen. I think you know what I'm going to do. I'm going to take 10.6 grams, multiply it by grams on the bottom, moles on top, 15.999. Do the math for that, and you get, and again, I have this one worked out for you as well, a nice easy one, 0.663. Now I'm going to stop here. I'm going to ask you. I'm not done. I have a second step to do. First step was converting the moles. Who can raise their hand and tell me the answer right now? What must the formula for this compound be? Given just this first half, you should be able to see it if you think about it. What do you think?
SNO2.
Exactly. Now some of you are looking like, how did he know that? How did he know that this guy is going to come out to be SNO2? Who wants to explain it? How did he know it's going to be SNO2? Emma.
Because if you times the SN5 to get the oxygen.
That makes no sense to me.
Wait.
Looking at these numbers, who can tell me? Well,
There's double the oxygen.
yeah, there's twice as much O as there is SN.
Okay, that's what I meant.
Okay. Maybe that's the way. Maybe that's what you're trying to say.
Yeah.
Okay. So this is a nice, easy one. I can already see what the answer is going to be. By the way, is it exactly double? If you were to divide these out, you wouldn't get exactly double, would you? But it'd be very, very close. It'd be like 1.99 or something like that, and that's fine. You could round off. These kind of problems, when you're dealing with experimental data, normally I say you cannot change significant figures. But here, what are we looking for? We're looking for the whole number ratio, right? So if you're close, if you're within, I'm going to go crazy and say if you're within a tenth, you're allowed to round it off. Because back in the lab, you're not going to be that good. Okay? So if it rounds off to be 1.98 or 2.01, it's really 2. Okay? Because we're looking for the whole number. But it's not always going to be as easy. So I got to show you the second step. The second step, how would I do that if it wasn't that nice and easy numbers like that with only 2 of them and no other complications? I would have to still, for harder ones, do this. Whoops. Do this. Divide each of those numbers, or however many you have, because a compound can have more than just 2, by the smallest number of moles. What's my smallest number of moles here? What's my smallest of the 2 numbers? Y'all agree it's 0.332? Right? Is smaller than 0.663? Okay. We're going to divide each of these guys by the smaller of the 2 numbers. And we're going to find the ratio. It's very simple. All right? Do it for the tin, and here's what you get. 0.332 divided by 0.332, you get 1. Do it for the oxygen, 0.663 divided by 0.332, you get 2. 1 to 2. Just what you wanted, just what you were expecting to find. All right. Now, at this point, you're basically done. Those are the 2 steps. However, you're not finished. You're going to lose a stupid 2 points if you don't do the next thing. If you leave your answer like that on the test, you're going to lose 2 points. Because that's not the final answer. The question asked me for the empirical formula. The empirical formula is not 1 to 2. That's the ratio. What's the answer? I heard it before. Somebody said it. SNO2. That's the final answer. So don't forget that stupid little thing for a big problem like this. You don't want to lose 1 or 2 points, however much I make it worth to not have the final answer, SNO2. All right. Well, that seems awfully easy. We're going to do this in lab tomorrow. We're going to be able to do this for hydrate, which we've seen 1 hydrate before. Okay, we're going to do that. But before we do that, I've got to show you how to do a much more difficult one. Okay, molecular formulas. Okay, Roman numeral 7.
May I have your attention, please? Any sophomore who took the PSAT with last names beginning with the letter H or M, please report to the conference room to get your test results. Thank you.
All right. Now, the molecular formula, you really want to be here for this. I know they're calling for you. You can go if I finish, whenever I finish, all right, or some other period. But this is the harder one. Remember, I just did an easy one. I think most of you could have figured that one out on your own. All right, it wasn't that bad. But the molecular formula is a little different. Notice when I gave you those initial compounds, I did not give you one that you're familiar with. I wrote down water, I wrote down carbon dioxide. I wrote down salt. I even wrote down a guy like Al2SO4 3. But I did not write down another guy that you're very familiar with that could have written the compound formula for back in September. What's that?
Sugar.
Sugar. I didn't write down this guy. Anybody want to tell me why I did not write down glucose as an example of an empirical formula?
No.
Josh.
You break it down more.
Exactly. That is not an empirical formula. That can be broken down into C. What's the simplest formula ratio of this? C1H2O1. Yeah, that's the empirical formula for glucose. That's the molecular formula for glucose. The molecular formula is the actual formula. The empirical formula is only the simplest ratio. Water's actual and empirical formula is H2O. So is carbon dioxide. That's nice. So is salt. But a lot of guys aren't like that, especially organic ones. So these guys here, I have a second step to do. Okay, and I'm going to talk, actually a third step to do it. We'll talk about that in a second. But let's give you the definition then again of this. The molecular formula is the actual number and type of atoms in a compound. It is not the simplest ratio of those atoms, which makes for a harder problem. This makes for a much harder, well, I say much harder problem. It makes for an extra step. I made this example much harder. I gave you 4 reasons this next problem is different. See if you can pick them out after you're done copying it, because it's a long problem to copy down. So copy this guy down and see if you can figure out all of the differences between this one and the previous one. After you're done copying it. Because there are actually 4 differences, and you're going to only notice probably 3 of them. The 4th one doesn't show up till about the middle of the problem. Okay, if you're done copying that, who wants to raise their hand and tell me what's one way this one's different from the previous one? How is this guy different? Some of them are just basic, easy differences that you can spot pretty easily. What's that?
There's 3 elements.
There's 3 elements instead of 2. And I could have 4, 5, 6 elements. I mean, it depends on the compound. So that's one thing. That will not change a whole lot, but that is different. What else is different about doing this one and the previous one?
There's percentages.
There's percentages instead of grams. That would certainly cause you guys problems, but it turns out to be one of the easier things. What else?
There's the molar mass.
It gives you the molar mass and asks you for molecular formula. Both of those are related to each other. There's a reason for that. That is a big difference we're going to have to do at the very end. And the 4th difference you can't see. Okay, but there is a 4th difference you're going to see in here in a minute. All right, now this is the tough one. This is the one you really want to pay attention to. Okay? All right, let's try this guy. We'll do it together. I'm going to start it the same exact way. And immediately I would run into trouble if I didn't realize that percentages are not a problem. If I'm given percentages, what can I assume? What sample size could I assume that would make those percentages be nice and easy and I could use the exact same numbers? What sample size? If I'm given percentages, I can assume any sample size. I need to convert grams to moles, right? What amount could I assume we had in our sample that would make these numbers very easy?
1.
Not 1, even easier than that.
0.
100. 100. Why? What's 40.9% of 100 grams? 40.9 grams. What's 4.58% of 100 grams? 4.58 grams. So in effect, people, what do you basically do to the percentage sign? Change it to a G. Change it to grams. Because I can assume any sample size, right? If I'm told I have 4, the previous problem said you had 39.6 grams of tin. You know what this problem is saying? You got 40.9 grams of carbon if you assume a 100 gram sample. And that's not a problem. So let's do carbon here first. Carbon, 40.9 grams. I simply change the percent to grams. So like I said, that's why you can change it, but that's all you have to do. So it turns out to be not a big deal. I convert grams to moles. 1 mole contains how many grams of carbon? 12.011. That's from the periodic table. And I need people to help me on this one, so get your calculators out. Jared, you do that first one, and while he's doing that, let's do hydrogen. I've got 4.58% of hydrogen, but since I'm assuming 100 grams, I'm going to have 4.58 grams of hydrogen. Grams at the bottom, moles at the top. 1 mole contains, for hydrogen, 1.0079. That is the molar, the atomic mass of hydrogen. Let's let Ronnie do that one. And while she's doing that, let's set up O. We've got how many grams of oxygen? 54.5 grams. Grams at the bottom, moles at the top. 1 mole contains 15.999. All right. Josh, you do that one. All right. And while he's doing that, let's go back and get carbon. What was carbon, Jared?
3.41.
Correct. 3.41 moles. What was hydrogen's?
4.54.
4.54 moles. And what was Josh oxygen's?
3.40.
Well, it's 3.41 when you round it off, I believe. Moles, right?
Yeah.
All right. Now stop. I'm gonna save yourself a little bit of time here, people. You do not have to do a whole separate problem rewriting out carbon, hydrogen, oxygen. I have to divide by the smallest number, correct? Let's just do it right here. You have room, don't you? We'll just put it right on there. What's my smallest of the 3 numbers here?
3.41.
3.4. So I'll divide by 3.41 here, 3.41 moles here, and 3.41 moles there. Okay? And I'll get 1 for the top answer, and I'll definitely get 1 for the bottom one. What do I get for the middle one? Do that on the calculator. You also get something like 1.33, right? That's the problem. This is the hidden problem in this problem. Told you a minute ago, percentages were the problem. Not a big deal, just change it to grams. The fact that there's 3 of them, did that make a difference? No. I just did the same thing 3 times instead of twice. But this is a big deal. I got 1 to 1.33 to 1. I cannot just round that down to 1 or up to 2. I said if it's within a tenth, and even that's stretching things, you can round it to the nearest whole number. That's not even within a tenth. All right? That's bad. Now, at this point, I know the answer. You know what the answer is? The correct answer, don't write this down, is C, 1, H, 1.33, O, 1. But there's a problem with that. What's the definition of the empirical formula? Because that's what I'm trying to find here first. The simplest whole number ratio. This is the ratio. The ratio is 1 to 1.33 to 1. It's just not in whole numbers. Is there a way I can make this ratio, keep the ratio the same, but make them whole numbers? What could I do? Exactly. You're going to have to multiply by this guy here. Make him into a whole number. What's the smallest number I could multiply him by so that I would be able to round him up into a whole number? 3. If I multiply him by 3, I'll get 3.99. That is within a tenth. And that will be 4. 3.99, we would round to 4. But if I do that to him and I want to keep the ratio the same, right? I got to do that to everybody. Right? The ratio 3 to 4 to 3 is exactly the same as the ratio of 1 to 1.33 to 1. It's actually exactly the same as 6 to 8 to 6, right? If I multiply by the same number, I'm always going to keep that ratio, as long as I'm multiplying by the exact same number. All right, now, some of you, again, this is a long problem. Some of you are saying, okay, we got that. That was not fun, but we got it. But maybe you don't. Maybe I'm looking to see some faces that maybe don't have that. Let me do a few more of these, just real quick, okay? Watch. Say at this point, because I have one more step to do. Say at this point, I got 1 to 1.5 to 2. That's what I got for that same answer. What would I have to multiply everybody by? 2. Everybody see why I have to multiply everybody by 2? That's the guy who determines this, right? So your answer would be 2 to 3 to 2 to 4, right? Yeah, it's a nice form. How about if it came out to be this? 1 to 1.25 to 1. Everybody see why I have to multiply that guy by 4? Again, it's this that determines it. What's the smallest number I can multiply him by to get me close enough to round up to a whole number? What if it were 1 to 1.98 to 2.04? I would simply round. This is exactly what's going to happen to your thing tomorrow. You are not going to get perfect numbers. It's going to be 1 to 2 to 2. You see it?
How can you do that?
I just said how you can do it. I said it multiple times, Emily. I'm going to say it again. If it's within a tenth of a whole number, you can round it to that whole number.
What if we have like two that are like 1.5 and 2.8?
You won't. That will not happen.
Okay.
That will not happen. All right? Okay? So that's my point. My point is, do be careful of this. You're going to be close to within a whole number sometimes. Don't try multiplying it by 185, okay? That does not have to happen. You know, you're not going to be doing something like that. You're going to just simply round that guy up to the nearest whole number. And you couldn't do it for those other examples I gave you, 1.33, 1.5, 2.25. I'd have to multiply there. All right, but I'm not done yet. Hold on. Back to this problem. Now I know the empirical formula. I told you this was a long problem. The empirical formula is C3H4O3. All agree? Correct? Because that's what it was. 3, 4, 3. That is the empirical formula. Unfortunately, what did the question ask me for? It asked me for both the empirical and the molecular formula. The molecular formula is the actual formula. Guess what, people? The actual formula could be C3H4O3, kind of like water. H2O is H2O, period. Or it could be C6H8O6. Or it could be C9H12O9. You see what I'm saying? It could be any version of that as you go up. You all understand? How do I know which one? How am I supposed to know? What tells me that? There's one other piece of information that's in this one that wasn't in the other one, remember? Molar mass. No. I heard someone say charges. No. This is doing it differently. Remember, if I wanted you to just use the charges, there was no reason to go through all this nonsense. That's probably going to be your... You can go right now, in a second, so I finish this up. So you know what I got to do? I got to do this, people. I got to find the molar mass of that compound and see how he compares to this one. If I find that molar mass and he comes out to be exactly 176.13 or very, very close to that, then I know my answer is that. Let's do that real quick. How many carbons do I have? Matter of fact, I'll do it on, so you can see it on the thing. I'll do it on your page. Okay, so for carbons, I've got 3 times 12.011. For hydrogens, I've got 4 times 1.0079. And for oxygens, I've got 3 times 15.999. Real quickly, I need you to do those fast. Give me that first, and whoever gets the first one. Jared, you do the somebody else do the first ones in the middle one. Anybody get the first number, give it to me. Well, I know that one. That's actually 36.033. Right, that's easy. What's the next one? 4.0316. And the last one?
47.997.
All right. Add them all up, you get 88 point what? Quickly, hurry up. Add them up. Come on. 0.06 around there. It doesn't matter if significant figures at this point. We're doing this really quickly. If it's 88.06, what am I going to do with that number now? To find out how it's related to that number. Well, no, I'm going to actually divide it. I'm going to divide the 88 into that and see how many times he goes. If he goes in, how many times will he go, by the way? 2 times. So my final answer is, I got to multiply everybody by 2. My final answer is C6 H8O6. That is the molecular formula. And that is how you do these problems. Yeah.
Is it always going to be like a clean number like this?
Again, it will be